thing moves at lightning speed. You have some stuff and it's in production within months. That's kind of how the world works these days. But also, reasoning is all the rage these days. And even 2 years ago, or a year ago, we had a paper showing that you could do like multimodal versions of this reasoning. So if you're going to solve a geometry problem, you can go and just kind of sketch like we would do. You can draw a line for a tangent. You can sort of change the image and manipulate it and help think in image space. We use tools for doing this, but you could imagine trying to do it natively in the model too, allow different kinds of reasoning. And then we heard yesterday also a lot about inference scaling. We'd like to get all these sort of cool reasoning patterns that are happening text only to be much, much more general. And here's just an example of reasoning in the input, but you could do it all different ways. But in this talk, I'm going to mostly focus on architecture. And so I'm going to think about like specifically, what do we do to our transformers to build these kind of models? How do we set things up? And it's kind of a little bit, I'm a big proponent of open science. And it's a little tricky. So for example, here, Gemini is leading. They've got some models that can do really good versions of these things. GPT-4o is another example. This figure is from the Gemini 1 paper. It's kind of the last information we had about architecture in the public domain. Right? We'd like to fuse things. We'd like to have one single unified architecture for everything. About all I know from this figure is that their decoder wasn't fused. The input was fused, and I don't really know much else about what they did. And so at least, I won't necessarily be at the biggest scale. I won't necessarily be competitive with these methods, but we'll study how things scale. And we'll be open, and we'll try to share everything we're doing as much as we can and try to build a foundation for understanding these models. Before I get into the architecture, I need to talk about tokenization. I need to talk about the very basics that we're going to build these models on. And so if you haven't followed image generation, there's kind of two schools of thought. You can sort of use discrete tokenization. That was kind of the DALL-E 1, Party, and now XAI kind of line. There's definitely models still doing that, although it's not as dominant. Or you could, of course, do diffusion models, which everyone knows about. They've taken over the world, DALL-E 2, through all the stable diffusion, all these different models now. And there'll be some real trade-offs. And a big part of my talk today will be about sort of thinking about how do you integrate across these different ways of thinking about how to do this generation. How do you integrate this with the text more deeply? But to a first approximation, without getting into any technical details, if you're doing the token-based approach, what you do is you train an autoencoder. And what the autoencoder does is go from the original image to a sequence of discrete tokens. Okay? So this could be 1,000, it could be 4,000, it could be 500. It's generally a pretty large number. And then from that sequence of discrete tokens, you can map back to the image. Right? And this is called tokenization. It's often done as a pre-processing step. So you do this completely independently of whatever model you'll want to train later. That model I was talking about earlier. This would be done independently. And then you'll build everything on top of it. Okay? And there's tons of companies that will do this, and this is from one of the early ones, but even though you're using discrete bottleneck, you can get really good reconstruction. So you can get really high quality images back if you use enough tokens. Of course, then, the sort of more dominant paradigm now is to do diffusion. But of course, when you do diffusion, you also have a tokenizer. You don't do diffusion in pixel space. So you also learn an autoencoder. You take your image, you compress it down to a small number of, actually confusingly also called tokens as an NLP person, but they're not discrete. Okay, so these are embeddings for patches. They're real numbers. They're optimized, and then you reconstruct the image. And sort of without loss of generalization, because it's continuous, you can often compress a lot more. So maybe you'll have fewer patches. Maybe you won't need 4,000. Maybe you'll need 16 or 32 or 128, something like that. Okay, and so that's kind of the background. That's sort of what we need to know to think about how we go about building our models. Now what I want to do is take you through a series of models, 1, 2, 3, where we think about different approaches. So on the first approach, we're going to try to discretize everything. We're going to take that first tokenization approach, and we're going to say, well, an image is just kind of words like text. And that's going to allow us to unify things and get some really general models. But then we're going to, turns out, maybe have some little trouble with scaling and efficiency. And I'll tell you about that as we go. And we're going to switch to sort of a hybrid model, what we call transfusion, which is a hybrid of transformers and diffusion, which sort of gets a little better results and mostly is much more efficient. And then with whatever time I have left, not too much at the end, I'll throw in a little bit of with an architecture to get more efficiency and better generalization. Okay, that'll be the last part. So let's talk about the discretization approach. We called this model Chameleon. It was about over a year ago now. The beautiful thing about this approach is if you pre-train your tokenizer, then what I do is I just look at my data, and in multimodal data, like I showed you at the beginning, the documents have images and text in them. Maybe they came from the web. And I just download all the images on that page, and then I just tokenize them into discrete tokens. I just shove those discrete tokens right where that image tag was. And now to me, it's all text. I'm an NLP person historically. I'm just going to model everything as sequences of discrete tokens. And I'm going to just apply the GPT scaling recipe. So I will just rewrite all my data. I'll do all the steps exactly as you would do. I'll have a pre-training step. I'll have an alignment or post-training step. Any of the tricks like retrieval, augmentation, RAG, any of that, it's all going to work. It just basically comes along for free. I mean, we wrote a bunch of papers. There was work to do this. But conceptually, it was all actually very, very simple. So just to say that again, the first step in some pictures, literally the transformer here is the exact same. It was actually specifically the Llama architecture. We use the exact same code you would use to train Llama. And all we did was went through our data and rewrote all the images tokens, and then you get mixed sequences like this. And then to use this model at inference time, you literally just generate exactly as you would from a text-only language model. And then as a post-processing step, you take your sequence of discrete tokens that you know are in the image token vocabulary, and you run it through your detokenizer that you trained as a pre-processing. And that's it. The model figures out when to switch modes. It figures out what it wants to do. It figures out how to generate everything. It all just kind of works very beautifully. Okay. We did a bunch of studies of this kind of work. So, when you train big models, the hope would be, that we'll see the same kind of scaling trends as you would see, with GPT and other models. So we, of course, did our scaling laws. There's some, I won't go through this in detail. You can look at the paper if you're interested. You have to add some extra factors to the power laws for what modality you're in, because different modalities scale differently. But otherwise, it works kind of exactly as you'd expect. We also did, your standard post-training. We didn't get into the RLHF too seriously. You certainly could. But even just the first stage of massively multitask fine-tuning, basically take any task you want that has any combination of text and images on the input or output, image editing, various pose estimation, whatever you can formulate as just a mixed sequence as input and output. You just kind of throw it all together, you fine-tune on it, and you get really cool generalization. So the model is able to do all kinds of new tasks that I hadn't seen before. And here's just a quick example of that. The images aren't super high quality here because this was an older model, but it works really well, and you didn't have to really specialize for the different things you wanted to do too much. I mean, you have to collect the data sets, but that's mostly it. And then finally, one more trick, you can do retrieval augmentation. So this is an area where I spent years of my life in the text only, kind of thinking about these models. Well, it turns out it works for multimodal too. This example here is a little bit complicated, but just looking at the bottom row, if you took a state-of-the-art model at the time on the far right, it didn't know what an Armenian church was. That's kind of long-tail knowledge. It has a particular kind of steeple. But if you retrieve one image of an Armenian church and put it in context for the model, you can put anything you want in context. It could be image, it could be text, whatever. Based on the approach, suddenly it's able to start copying that style and generalizing it to other images. So sort of everything comes along for free. But now we asked ourselves, okay, can we scale this thing up? So are we going to get sort of these really cool behaviors at large scale? We have a large team doing this work. There's about 30 plus people, and we targeted trying to scale up to about 10 trillion tokens. Where for us, you see this mix here. Remember, an image is about 1,000 tokens, okay? And I won't take you through sort of all the pain of doing this, but the sort of summary of this slide, I'm not going to take you through each of these individual graphs, is that it was incredibly painful. Like months just kind of dealing with all the sort of numeric stability and scaling issues that come up. And it's sort of frustrating because, we had done our scaling laws. So we had trained tons of models up to, maybe 1B scale or something. We'd done all the plotting. And then we go to 7B scale, which I'm showing you here, and things went crazy. You would train the model. I mean, you'd have it training on 1,000 GPUs for weeks. Everything would be looking good, and then it would just kind of slowly diverge. And you'd go investigating, and it turns out your norms started exploding like 25% of the way through training, and you have to start all over again. And you have to wait a few weeks. And it's just like this, the science of how to do this is a disaster. Right? And so you go and you fix it by doing lots of norms and dropouts and z-losses and other things like that. You can look at the paper for the full recipe. Finally, we're able to stabilize the 8B. And of course, it happens again at 34B. Okay, so this was a little easier to stabilize. We only had to add a little bit more. But in general, these algorithms were sort of, much, much more fickle and sort of hard to get working than we wanted. Although we did eventually stabilize training and you can sort of look at the paper for the full recipe. Others have copied it. It's a nice recipe. But I don't know that we really advanced kind of the science of how to do this. So my challenge to the more theoretical-minded folks in the room is like, help us figure out what the heck is actually going on here. Okay, so we've got more and more points in this space. There's been other papers that have done better jobs of it since, but it's a mess. And in the end, you get a cool model. So this is, again, that first example I showed you. This was pre-GPT-4o, which now does this much better than any of these models. But we sort of build baselines on top of the best models and sort of piece things together where we didn't have things that could do full-time standard. And we got some of the first results where we could really do this sort of natively interleaved generation and get models to work pretty well. Okay, so the summary of this first part of the talk is that you can get these universal models. You can get them to scale pretty well. You can get this general multimodal generation. But we ended up kind of both a really bad result, but also deeply unsatisfied with sort of how finicky it was and sort of the efficiency of its scaling. Okay. But others have followed up on this work, and in particular, I can't possibly list them all, but one really great example is the EMU3 paper. And not only did they scale it, they made the images much more beautiful. They sort of got it's essentially the same approach. There are differences. You should go read the paper, but I'd say 90% the same approach. And then they also even got generalized to video, for example. Because again, a video is just a sequence of images, and we can, this architecture, you can do arbitrary sequences of anything, right? But the real issue here is efficiency. So to get these beautiful images, they had to go up to 4,000 tokens per image. Right? And then imagine doing video with 4,000 tokens. I mean, of course, you do little chunks of images, but conceptually, video with 4,000 tokens, like, it just doesn't scale. Right? It's very, very general and beautiful, but it's not really that scalable. Not only that, but there's this extra confound, which is that when you do your discrete tokenizer, all the way back to that first slide I was showing you, that's a lossy process. So your reconstruction loss, there's going to be an upper bound on your performance based on that. Now, it's not that bad. I just showed you some beautiful images. Like, you can really get it to go, but that's probably part of one of the fundamental reasons of why this whole approach is a little bit more expensive, is because you're working around and compensating for that sort of fundamental limit of that discrete compression. Okay? So going forward, then we asked ourselves, instead of doing that so exclusively, what if we sort of said, let's think, diffusion models were going crazy in parallel while all this was happening. They're getting so good. They're getting so efficient. Of course, what if we didn't just try to tokenize everything? What if we think more carefully about how to properly sort of integrate these two modalities? There's two ways of modeling. We came up with this transfusion architecture, and what you think about this is kind of, well, some of your data is discrete and variable length, like text. And there, autoregressive transformers are kind of the right thing to do. We know that, right? But some of your data is kind of fixed length and continuous, like images. And diffusion actually is non-autoregressive. It has all these nice properties. So why don't we just do a mode switching model? Why don't we just do a model that, when it needs to, can switch back and forth between these two different modes and get the best of both worlds? Okay? And so transfusion is our effort, and I'm sure others could do better, to do the simplest version of that mode switching model. So again, images will be in patches, but you'll use the continuous tokenizer this time instead of the discrete tokenizer. And you have a single transformer backbone. So you'll share parameters entirely across this entire transformer block that I'm showing you here. And you'll just have a model that can sort of model all this jointly because of the shared transformer. And you sort of get the strength of the next prediction and the strength of diffusion kind of all mixed together. Now, the trick is you need to sort of think about training, think about inference, think about how to set it all up. But conceptually, this is fine. The modern diffusion models are using essentially the same kind of transformers as the modern language models. And in particular, we would use like the Llama architecture again here. And it works fine for diffusion. It's not a big deal. Okay, so how does this model actually work when you use it? It basically inference. So you're going through the text generating token by token. And then you hit a beginning of image token. You switch into a non-autoregressive generation mode. So you basically know how big your image is going to be. You lay out all those tokens. You make them all start as noise. And now you iterate perfectly. But every step of that diffusion gets to attend back to everything before an entire mixed model sequence. It doesn't have kind of local adapters like transfusion models often do. like diffusion models often do. You just have two different losses. You use your diffusion loss for some tokens, you use your autoregressive loss for others. It's a little bit great to have two different losses and have to balance them, but it's only two, it's not so bad. And we're willing to make that sacrifice for the generality of the model. Okay? All right. So what does this model do? In the paper, we have just tons and tons of experiments. I won't take you through them all here. I'll just highlight one or two. So you can play with different architectures. So that transformer block is going to be jointly learned, but you need to project the images into that space and project them back out. There you can use UNets, you can use linear projections, you can use other things. They all work pretty well. This is sort of various end-task accuracies. You don't have to look at the detail. But in particular, in addition to choosing the architecture, you can also choose how much to down project. So how aggressively how few tokens can you basically use for each image? And a down projection of 8 here gets down to actually just 16 tokens per image. Something very, very small. And it still works actually quite well. At some point it does start degrading, but sort of the efficiency here is really, really, really much better. Especially if you use UNets, which are sort of COM nets that have some repeated structure and make it a lot more efficient. Okay. And then the other cool thing in terms of architecture is that you can, when you think about what's going on with that kind of mixture of the autoregressive and non-autoregressive, you basically get this really cool causal structure in the self-attention. So the text blocks actually have that normal diagonal structure we expect to see, but whenever you have an image, you get this little bump out, right? Because the image gets to look globally at its patches as it generates, so you get these nice little off-diagonal blocks. And that actually turns out to be really important. So we did some ablations where maybe you didn't have that, maybe within the image block, there's just only a 10 left or right, that's fine. It's actually easier to implement. The engineering for this is kind of a nightmare. So, if you're not careful, you get into custom CUDA kernels and stuff. And it turns out actually that bidirectional really helps a lot. It really improves performance. You can look at the papers for the full details. But conceptually, like you have that information, why not use it? Okay. We also looked at scaling trends for this model. Here, this is training runs where we started entirely from scratch, and we compared very directly to Chameleon. So because we had both the models, we could do really nice controlled studies. And maybe it's not too surprising given the efficiency in terms of number of image tokens, but it really shows out in the overall scaling trends. So you get these big factors in terms of the x-axis here is always flops. So this is sort of like how much compute do you need to spend to get a good model under various metrics. And it's just much, much better across the board. Well, and we sort of didn't quite go to the same scale as we had before, but going up to 1 trillion tokens and 7 billion parameters, everything is great. And I don't specifically have a slide for this, but all those stability issues I was talking about before, all the exploding gradients, all those things, just gone. We don't really understand why, but something about the discrete tokens kind of interacting the softmax together with the text tokens and the image tokens caused some sort of internal competition. It caused things to go haywire. Actually separating out the objective and having them separate and not competing with each other seems to just make everything much more stable and much easier to do. And again, that's not a super scientific statement, but it's a very strong empirical observation. Okay, so I'm new to doing image generation work, so I'm just still in love with showing beautiful images. This is relatively efficient to train relative to state-of-the-art models. And now we sort of get our image quality up because we're building on all the state-of-the-art diffusion methods and relatively good sort of correspondence, so forth. Okay. So in summary for this second part, we sort of showed you that philosophy. In the beginning slide, I said we want to keep it as simple as possible. I would argue this is maybe a little bit more complex. You're having to do this mode switching, but still relatively simple, and it really pays off. Like it's really worth taking that transition. Makes things much, much smoother, makes things better, makes things more efficient. Of course, follow up after or sort of in parallel as we were doing this work, everybody knows now about the GPT-4o model. It's really amazing if you haven't played with it, and it's sort of one of its many claims to fame is this sort of image consistency. So here you can see 1, 2, 3, 4, 5, 6, 7, that this is kind of one sequence that's all generated. and the robot is coherent, it sort of has that kind of context and dependency and so forth. We don't know exactly what the architecture is. They were even teasing us, like if you remember when the press release came out, they had like a whiteboard with transformer and diffusion or whatever. So it's some sort of hybrid. It's almost certainly not just straight transfusion. It's something else. It has certain problems that this wouldn't have, like a lot of the fine details. If there was like a person's face, it wouldn't naturally perfectly match and things like that. So, but it's something in this space. And I think in general, we're still working out like what is the perfect architecture? What's the perfect way to set this up? But this is kind of the right rough direction, even if there's some noise in our gradient, if that makes sense. Okay, one more section to come. So now I have to tell you, what's missing in this approach. So actually, for both Chameleon and for transfusion, if you do a little analysis of the embedding space, where you have this shared transformer backbone, we would really like interesting cross-modal transfer. We'd like sort of the representations for the text and the representations for the images to kind of overlap and mix and kind of share information. But actually, if you do low-dimensional visualization of those for various data, various layers, and so forth, the details don't matter here. The main thing is that the different colors are the different modalities, and they're basically separated. And that's not what we were hoping for, right? We're hoping to get interesting transfer. It seems the model has basically used the same transformer to just kind of learn 3 different transformers, one for each modality. And actually, when I see that, that makes me nervous because I'm thinking about efficiency, and like maybe that was a waste to have them all together. Maybe I just wasted lots of resources. There was actually internal competition, and it could do even better if I didn't do that. Does that make sense? So that's what we did for our next step. We said, actually, let's just play with this. Let's see what's better. Let's separate them apart, see if we can get better training. So that's what we're calling mixture of transformers. And it's really the same exact model I just showed you. And this, I'll slow down a little bit here, just see if I can make this clear, and ask me questions at the end if it's not. It's a little bit tricky, but it's inspired by a mixture of experts, right? And so a mixture of experts, you have different, just in the feed-forward layer, you have different parameters, for different potentially modalities, or you learn the routing or whatever. It's all still the same model, right? It's all jointly trained. So we're doing the same thing here, but we're doing it for the entire transformer, not just the feed forward. So for each modality, we have deterministic routing. We have an entirely different transformer, but it's all jointly trained and running in parallel. So we're going to separate out the representation space, but they're not independent models. It's still one total same model. Does that make sense? And that's going to allow us kind of play with how much was that competition hurting us? How much could we have done things differently? Can we get better efficiency and so forth and so on? Okay, and I don't have too much. I'm going to show you some results and stuff, but this is it for the method. All right. So overall, what we actually found empirically, and I'll take you through some of this, but this is just a summary statement, is across lots of different settings. So you can do this for Chameleon or for transfusion. You can do this in other settings. You can include speech, other modalities. It just really helps a lot. So you could get sort of 3x plus efficiencies by doing this separation. So that hypothesis that we were getting sort of unwanted internal competition probably is happening. This isn't the proof, but you were seeing like a lot better training, a lot better performance. Just a few examples of this. So for what we're comparing here is sort of dense training, mixture of transformers, and then MOE. So we can sort of match capacity, right? So we have 2 different Sparch approaches, matching capacity versus the dense. They all have the same number of active parameters. And what you find out is actually for text, we didn't get that much of an advantage over MOE. MOE is really very optimized for text. It's kind of the right thing to do. It's fine. But for the image model, specifically when you separate out the image from the text, it really helps a lot. In some sense, they were probably just learning mostly independent anyways. And if you go ahead and embrace that and don't make them compete with each other with their gradients, it actually wins. And that's basically what you're seeing here. Here's a visual way of thinking about that. I'm just in love with these images. So this is sort of the dense versus the MOT trained sort of flop matched at a reasonable budget. And you can basically see again exactly what I said, but the images here, they've gotten better quicker. In particular, look at this one is much better. And so with the same flop budget, probably just you're having that competition, you're able to get things to learn much more smoothly. Okay. And then you can also play other tricks. So one bad thing about the things that we set it up right now is because we have the sort of same transformer shared across all the modalities, it also needs to be the same size. So, actually state-of-the-art text models in general are much bigger than state-of-the-art diffusion models. But now, since we've done this MOT and decoupled the parameters, we can actually think about starting to scale them differently. So maybe for the text tower, the text transformer, we can add an extra MOE, give it some more capacity, but for the image tower, we keep it the same size. So we can do like heterogeneous scaling and capacity. And there's much more work to do here, but we did some initial experiments, and yeah, that does seem to be a good idea. You should sort of scale differently as appropriate for the modality. Other things you can do on top of this, now that we separated across with the two towers, you can think about sort of initializing from previous models. So we've been mostly training from scratch, but of course, you shouldn't, at least for text models, you really shouldn't be in the game of training from scratch anymore unless you're sort of a billion-dollar enterprise. Right? That's just gone crazy. So what we can do is, have the tower for the text and have it completely frozen. You could also tune it a little bit. And then mostly focus on, again, it's that joint model. It's all running in parallel. It's all deeply fused and fully cross-attending, but you're only mostly training the image part. Okay, and this was an LM fusion approach that we did recently. This also works beautifully. You get more efficiency by doing it, and more beautiful images. And I think here you get a much more efficient result, essentially spending all of your time training the image generation model, but benefiting deeply from deeply integrating with the language model. Okay. So in summary, for this section of the talk, we're thinking about kind of when to share parameters, when not to share parameters. We're thinking about efficiency. We're thinking about trying to understand what's been learned, and we're able to get much better architectures. And I think it's an open question, really, how to best integrate across the modalities. But now we've got a few points in the space we can start thinking about, sort of maybe we're doing more fine-grained distinctions and so forth. Again, this is a fast-moving world. That was a pretty recent paper, but even like a few weeks ago, another paper came out that built on it. So this is the Bagel paper from ByteDance, and they basically took that LM fusion approach I just showed you. They, of course, made some changes. They made it better. They did a lot of really amazing data work that we didn't do to get really high-quality data for training the model, and they scaled it up, and it really works. So they get beautiful results. They get this kind of sort of consistency, all these different editing and so forth and so on. And one cool thing is they actually open source their model. So, I'm sort of a real proponent of open science. I wish we could open source more of our image generation stuff, which we can't for various reasons. And you should use this model. It's super cool. And we're building an envelope going forward too. This is how the community is supposed to work, and it's really, really exciting to see it happening. Just a little bit of discussion of future work. So, I think the idea that you have this really nice hybrid of autoregression and diffusion, a lot of models are just kind of racing into video, and this is one place where I think it would be really cool to follow up on this work and try to understand sort of how do you actually get things to work over long horizons, how do you get them to be consistent, how do you get them to be efficient. We don't have deep insights here other than it does run, like you can just do it. Could we do even things better? Could we understand it? How's the best way to do it? And then I would love to keep pushing on this kind of heterogeneous story that I told you a little bit about at the end. So, how do you think about the right scales of things? How do you do it without fully separating the models? How do you get the right level of integration, and how do you get the right scaling as appropriate? And I will stop there a minute early so we can have lots of questions and just leave up the summary. Sorry, this is a busy slide, but these are the 3 models that I talked about for summary. So thank you.
Someone running around with a microphone. And that way, when you ask your question, speak into the microphone so people online will be able to hear as well.
Yeah, super interesting talk. Let's see, I have a lot of questions. Let me just see if I just quickly summarize something for the question. So the first part, you're kind of arguing you have a fixed tokenizer, if I understand correctly, for the images, and then you train jointly, and you made this argument that there's possibly like a not a capacity issue, but you want to train jointly. And then the second part, you move to joint training. Granted, there's some differences with the diffusion loss, and that seemed to help. But then you went back to not doing the joint training on the text. So part of this is you're kind of saying, hey, actually, and all the MOEs, the joint training probably isn't really doing anything. So, the motivation for the MOE is get rid of, try to really restrict the joint training. And you went to the extreme of that, do no joint training on the images. And what I'm trying to get is this is something we've been thinking about here too, your intuition for what part of the joint training is helping the images? Because you didn't do hey, I'm going to do separate image training too and try to bolt them together. So what's your intuition for...
Actually, we're going to try that next.
yeah. So what's your intuition for where the joint training might help? And is it the tokenizer level, or do you want to bolt?
Yeah.
Because you kind of went back and forth between...
Yeah, I have a few ideas. Okay, so a couple clarifications. So the tokenizer is always pre-trained independently and never jointly trained in any of the models. It's just sometimes discrete and sometimes continuous. But even latent diffusion, you pre-train the tokenizer, it's a separate thing. I'd love to work on that on a separate project, but that's just not what it is. And actually, in every case, except for maybe the LM fusion right at the end, everything is jointly trained. The main thing we change is whether you're sharing representation space or not. So everything, the way you could think about these models, there are a couple different things you could want. You could want joint end-to-end backprop, like gradients are flowing through everything. You could want everything to be able to turn to everything without any submodules. And you could want a shared embedding space. Okay, so the way, whatever the embeddings are, is the same for all the modalities. So in Chameleon, we did all three. And in Transfusion, we gave up the also. But then in the mixture transformers, where we separated things, we gave up them into different embedding space. But we kept it up here, actually. So it's all fully optimized. It's all fully cross-attending. But we gave up on one piece of the sort of joint training that you might want. And it seemed to have really helped. Now, I think ultimately we should put it back somehow. But it should be limited. It should be carefully done. And we should sort of actually see the gains and the transfers from it. And I don't know how to do that yet. This is great. Thank you.
I have a question about your thoughts on maybe one possible source of issue with the tokenization approach. It seems like you're throwing away a lot of structure in the data by tokenizing images. In particular, there's things like spatial locality, like this pixel is related to these. And also you're throwing away the real number distance structure. This intensity of red is related to this slightly less intense version of red. Do you think this kind of thing matters?
Yeah, that's a great question. And I think it's relevant both for the discrete tokenization and the continuous tokenization. It's because they're all bottlenecks. They're all compressing the image and then reconstructing it. Those tokenizers are trained with the reconstruction loss. So all those factors that you mentioned, given your finite capacity, if you do a better job of keeping that image representation, that's what it's trying to optimize for. So as much as it can with the capacity you give it, it will try to remember all those details, but it's not guaranteed. And that's why something like end-to-end training of a tokenizer or something could be better potentially. But this is just kind of where the field is. And I think, if you don't work with diffusion models, you probably often don't even realize that to do latent diffusion, you have this tokenizer that you've pre-trained, with a reconstruction loss. And that's just a fact. And it was relevant for this talk because I really want to kind of tease apart exactly what we're doing on top of it. Yeah.
Here. Thank you so much for the great talk. I have a couple of questions. Sorry, my thoughts are not super well informed yet, but
that's great.
It's about the mixture of transformers part of the talk. And basically, I was wondering how much of this you think is related to the aspect of scale, and also how much of it is related to the availability of data in different modalities, and also the semantic similarity in data in different domain. So I want to also provide like a little bit of contextual information of why I'm asking this question. So we have done some research in cross-lingual transfer, which obviously is quite different from, cross-domain.
But usually a better transfer, that's right. Yeah.
But I wonder, so one of the things that we observed was that when we have cross-lingual transfer, when we have more data with celebrities, data that's present across different modalities, actually we have representations that collapse across different type of data, and it also leads to better generalization as well. But when we don't have that, that doesn't happen. And we also observe that across different kinds of scales, we observe very interesting patterns in terms of how much we see representations kind of have similarities across different languages. So again, I know different languages are very different from different domains, but I wonder, how you see that.
Yeah, actually, this is great. We've worked a little bit multilingual a few years ago too, and I think you could think about analogies between languages, between domains, between modalities. And in some sense, something beautiful about the multilingual setting is like, you just take a bunch of French documents, a bunch of English documents, a bunch of other languages, even if there's no bytext at all, somehow it learns transfer. And that's what we were hoping to see more of in the multimodal setting. That was kind of the ethos. If you're an LLM person, that's what you would expect to see. And then, sort of we met the reality of the world, basically. It just didn't happen as much as we were hoping. And so it's still a cool architecture. It's still, it's still nice. Like if you talk to people that serve stuff in production at Meta, they'll be, even if it's not better, if they can only deal with one model, they might be quite happy with that, as opposed to MOT and stuff where we're sort of separating things more. So for me, this is more about like the science of trying to run controlled experiments. So a lot of what we did was kind of try to do real deltas, and it's hard, and we didn't do it perfect. But you're absolutely right. Like the scale you do it at, the exact data you do it on, all these things really crucially matter. And I can't promise that like somebody's not going to come up with a more efficient, discrete, adaptive tokenizer and do it at a bigger scale. I mean, maybe it's even what GPT-4 is. Like, who knows? And I think it's cool. I mean, I think it's fun. It's like an unresolved area. We're in the middle of it right now. I don't have the perfect answer yet.
Yes, great talk. I just wonder, what do you think, what are your hypotheses? What would make, like in what's called transfusion, what would make different modalities collapse, like with multilingual? Would it help if like there is more text in images? There must be some connection, right? When it's like probably multilingual because there are some bilingual text that would help.
Yeah. So what would actually help the alignment? I mean, more calculus could help a little pretty quickly, but we do train on a lot of image caption pairs. So we do actually have a fair amount of like comfortable across the modalities, and that wasn't enough. I mean, one interesting question, and I think I've had these discussions with language and vision workshops and stuff over the years, is what do we actually expect to transfer from images back to text? Entirely clear, actually, when you think about it a little bit more carefully. It's not as obvious in the multilingual case where you can translate. It's the same underlying concepts. So maybe we could get some physical common sense. Like for example, I would love to eventually get a model you can train on video, and then ask it questions in English about physics, and it does better on those questions. But that's actually a much further transfer than say, how do you translate words from French to English or something, right? And so, we were hoping for things, and it was sort of a bit of a fishing expedition, but in hindsight, and I kind of knew it going into it, so we knew the right things to look for. Like we were, there was higher uncertainty, but it's actually not entirely clear what you do expect to transfer. And that's kind of fun. I'd love to have conversations during the rest of the day. Maybe some of you all have some ideas, and we could poke around, because probably what's happening is some things are transferring and some things aren't, and it's a big messy soup. And that the dominant factor is the transfer isn't happening, but I bet if you look, you could find some. And when we haven't done it.
No, on the same topic, I would say. So it seems to me like language is just a much more efficiently learnable, efficiently compressing sort of modality for representing, state of the world. So I guess sort of building on that, do you actually think that there like that even the methods that you are using to try to measure the degree of overlap or alignment might be intrinsically favoring the more information, let's say information dense modality in the first place. So is it like how much can you even measure alignment given that one of the modalities is so information dense and the other is so information sparse?
Beautiful question, absolutely. And actually, if you pay, I went really fast, but actually we did no explicit experiments to try to measure that, and it's a it just didn't get to it. So what I actually showed you was things like training speed and training stability and end task accuracy, and that's because fundamentally I'm like an architecture guy more than I am an analysis guy. And actually, we need better. And I share your intuition that it's going to be different for density, but I actually don't know how to measure it. And it's a really, really great point.
Thank you for the nice talk. I had one question regarding, following up on Naomi's question on the alignment. So what you showed with the PCA and the alignment on the PCA is absolutely like typical of one of the footprints of what we also see in VLM, like CLIP, whatever, AMV2, where the first component are often encoding the modality, and the juice, like the really multimodal concept, are not in the first component, but are after, like when you look on the lower norm, if you want subspace discovered by the SVD or the PCA. So have you done any like more study or like trying to compute some sense of alignment that would be independent, as Naomi said, of those kind of bias?
Sure, yeah, that's a great question. We haven't tried. I think for a contrastively optimized representation, you could think of this as sort of a autoregressively optimized representation, if such a phrase exists, right? Like we're just sequence modeling everything. So we would expect it to behave a little differently than CLIP, maybe, because it's not most of trained. But yeah, you make a good point. If we did a better analysis by factoring out the predominant modal factors, maybe we would find it. And we didn't. And it's a good point. Thank you.